it away.
Hi. As you said, we're the Resilient Renewable Electric Energy Systems team, and I'm Joseph Chody.
I'm Alex Mustaine.
I'm Nathaniel Chandra.
I'm Guoyang Chen.
So why should we monitor the power grid? Power outages are too common, they take too long to fix, and they can be life-threatening or equipment damaging. High voltage can damage lots of motors, and low voltages can put people relying on medical equipment at risk. So what does the grid do now? So at the moment, the grid attempts to detect outages primarily through people calling in on a phone call. The smart meters, which monitor the grid, are primarily there to increase price transparency and tell people how much money they're spending and when they're spending money. On the prevention side, rolling brownouts are often triggered to prevent an full outage, and monthly maintenance is often run to prevent fires. But let's look at an example. So here's what can go wrong in 15 minutes. A line clamp fails and starts dropping hot metal. The line starts a small fire. This fire continues to grow unnoticed. The fire engulfs a hillside, and then a concerned citizen calls 911. So all of that time is time we could respond faster to the outage and the potential damage if we had more information. So could we detect the line clamp failing? The power grid, when it's operating normally, is pretty predictable. But when the line clamp starts to fail, the line will experience current fluctuations. There's a lot of research on this. And so the question is, what if we had this data? Could we, before the line clamp failed, intervene in this incipient failure period where there is data showing something's wrong, but something has not caused an actual problem? On the next slide, we'll see that SEADS 1 attempts to help with this problem by gathering that data. It gathers 8,000 samples a second. It uploads this data to our servers every 5 seconds, and it gathers 138 gigabytes of data per day at 100 devices. So that's a lot of data. As compared to a smart meter, which is only sampling once per 15 minutes, it's uploading its data every few hours, and it's uploading a meager amount of data. So our device improves in many ways, including cost. As you can see, the SEADS 1 has a device, a AC monitor, and then a USB cable and plug to provide it power. The SEADS 1 is composed of a custom DC header and a Raspberry Pi, and monitors an outlet while gaining power, hopefully from a backup system, so that even if the power goes out, we still get the signal that the power went out. This device is connected to our servers via Wi-Fi.
So next I'll talk about the general phases of our project. So previously the SEADS phase 1, that's the device that was built. That's basically a proof of concept and to show that we can have sensors that gather the data that we need. And what we're working on right now, SEADS phase 2, is primarily like the data communication and storage, along with the UI and outage notifications. And this is about actually having all that data accessible. And the next phase after that is the phase 3, which is outage prevention, which is performing analytics on that big data to see if we could predict a power outage before it even happens. So there were some issues with the previous phase. So basically the website kind of failed. The graphs were pretty broken. There's no account system, so you can't really manage a device. And your homepage took over like 30 seconds to load. And on the software side, there were other issues where the devices started crashing and not being able to upload data. And the code was not well documented, so people couldn't build on the past project. So with all this data, there were some problems. Most of all, the data is basically boring. You have like days and weeks and months of constant voltage, right? Because your power doesn't really go out that often. So you'll just see data points at like 120 for the longest time. And also, there wasn't really a way to urgently react to a power outage or a power fluctuation. So if the power spiked up or down, we wouldn't really be able to know about it in the previous phase. And also, the data wasn't really just user-friendly. There was no way to visualize what was going on with the data. So phase 2, SEADS Vault, what we're working on right now, aims to like fix that part. So there were issues with the data freezing or stalling because it couldn't handle that over 100 gigs per day with each 100 devices. And there was no way to analyze the data. And like we said before, the documentation is pretty poor. So in order to solve this, we were able to calculate and detect when an outage happens based off the IEEE standards for event recognition. And also it was very quick. We were able to quickly see that event happens, and then we can notify people at their preferred communication method like email or text that a power outage actually happened. And most of all, it's pretty. So that way you can present the data in a nice format and you could easily read it. So how does your data become useful? So as you can see here, phase 1 on the left here, this was a previous project where the SEADS devices collect the data and then upload it to the database. And here, what we worked on, SEADS Vault, connects to that database and filters and analyzes that data. And we put a nice API layer on top of that. So that way you're able to be notified by text or email, say if there's a power outage at your device, and subscribe to other devices around the area. Say if you want to subscribe to like your daycare or like a school to know when the power goes out there. And then you could also graph the data. We have a graph showing the voltage fluctuations over time and a log of events that occurred. And we also have a way to visualize all the devices in time and space on a map.
Next, let's have a walkthrough. As a user, I got my new C device, and I can find the installation instruction under the About page. Next. Once installed, the user can sign up for an account and register the device to it through the Auth0. Next. The user can add his personal information and subscribe outage notification by email or SMS message under the profile page. There are also device cards to register new device and to view the detailed device. On the register page, user can input the device information and the geolocation. Then the user will be able to see the available devices on the map on homepage. On the device page, user can view the voltage data over time and the voltage history. When the outage happens, the user will receive an email notification showing the device detected an outage at what time and where. Next, Nathan will introduce the SEADS board.
So let's look at what goes on in the backend. On the back, we're storing the user's account ID, device PIN, and contact for the notifications. We then archive that voltage history to generate a device timeline so we can look back and look at what we can do with it. For our analysis, we follow the IEEE standards to convert voltage into some status. Finally, we improve on the previous project by adding a cache in order to optimize our queries to make the backend go faster. Next, on our application programming interface, we use a variety of third-party APIs such as Auth0 for handling login and register, Twilio for sending the email notifications, and Mapbox for our front-end map visualization. We also integrate a lot of security through a connector that allows us to access the database safely. And we have a cursor so multiple users can talk to our database without overloading it. Next slide. Let's talk about some spikes we incurred during this project. Originally, this project was 2 projects merged into one, Rrees Microgrid and Rrees Power Grid, where the microgrid focused more on the consumer end and the power grid focused more on the power companies. In addition to this current quarter, we've dealt with the coronavirus. This made it a lot more difficult for us to schedule as many of us moved back to our houses, some living in the US and some living in China. In addition to this, the lab was closed down, so we couldn't have any more live devices out on the field. And finally, there was a lack of documentation for phase 1, which really made it hard to get the ball rolling. Next slide. So let's talk about the progress we've made. We were able to create software as a solution for outage detection that uses the SEADS hardware, and we improved on the previous project by making it quick and secure. Our solution handles big data, has outage notifications, and is very user-friendly with a quick response. Next slide. Now, using this data, we can talk about the future for outage prevention. Our data should be able to be exported so scientists and researchers can develop machine learning models for the waveforms. you compare the waveforms to faulty equipment and the transformers in order to find where they are, and then tell service providers such as PG&E the location of the transformer in order to get a fix before it turns into a fire. Next slide. At the end, we'd like to thank our contributors, Brian Zhao for developing SEADS Phase 1, Patrick Manti for mentoring and sponsoring and telling us this idea, Jeff Lefevre for creating Skyhook, Michael Choi for building the SEADS hardware. And for this class, we'd like to thank Aquila de Silva for helping us with our Scrum the first quarter, Faiz Brahman for helping us during the last quarter, and Richard Julik for checking in and making sure we were on task. Thank you. Any questions?
So thank you very much. Rrees, I don't quite know how to pronounce that, so I'll just say Rrees.
Rrees.
All right, thank you very much for that interesting extension project.